November 1. Here we go. All right. Happy Monday, week 3 Monday. We're going right along. Okay. Today we will discuss random number generation. Okay. So far, what we have said is, we have Bayesian statistics. And in Bayesian statistics, we treat our unknown parameters as random variables. However, when you do that, a lot of the things that you want to figure out and solve become a lot more complicated. And so the way we're going to try to solve these things, rather than doing them analytically, is we're going to estimate them using Monte Carlo integration. And we said, okay, well, we have a way to do Monte Carlo integration. If you want to get the expected value of a random variable x, and you apply the function to the random variable x, you can do that. You just draw random values from that distribution, apply the function, and then take the average. So that's simple and straightforward enough. But all of these things that we've done so far have really depended on our ability to generate random values of f from this distribution f. Okay, so far we've been able to do it because so far the random distributions we looked at were things like the uniform distribution. Okay, and then we also had, what else do we have? We had the normal distribution, the beta distribution. So we've been able to generate these things because R has these functions that generate random values. Okay, but a reasonable question is, well, how do we generate these values in the first place? And what if we want to generate values from something that R can't generate? Okay, and so that's what today's lecture is going to focus on. Okay, so pretty much all of the algorithms that we will look at for generating random variables will start with our ability to generate random values from a uniform distribution. So we're going to start off with this thing where we can generate values from a uniform distribution. And this idea of generating random numbers used to be kind of like a really tough job, okay? And because you would need some kind of like mechanical appliance. So you would have like a wheel, and you would spin the wheel, and it would land on from like 0 to 10 or something, or 0 through 9, or you roll a die, you do something, and if you wanted random numbers, it would be tough. Now, so you could buy books of random numbers, okay? And they have kind of, just for historical legacy, you can buy this anniversary edition of 1,000,000 random digits, okay? So this is an actual book you can buy, and this is a book that was published back in the day. Oh, they got rid of the preview pages. Okay, well, it was just random numbers. But you could actually purchase basically a reference of random numbers, and then if you wanted to do simulations, okay, it would be something like, okay, I'm using this particular book, and instead of a set seed, it would say like go to page. You would just write down, I started on page 215, row 1, row 1. Or you'd say I went to page 324, row 25. And that would be kind of like, this is the first digit that I used for my random sequence. And it would just be a sequence of random digits, and people would use that for their kinds of simulations. But now, we have computer programs to do this. Oh, okay. Oh, I put this slide in here. This is stupid, but I do. There is this question of, is anything truly random? And I don't know. I think, right? I mean, this is like a philosophy question, and I don't know if we have any hard determinists here in philosophy, but you have. Is there, randomness, or is everything deterministic? Because if we talk about some, we often think of coin flip and rolling a die truly as like random events. But if you knew the exact force applied to the coin and like the exact kind of physics equations going into the coin, you should be able to like predict how the coin would land, right? If you knew the exact amount of force, the rotation, I don't know if there's air resistance and, whatever applies, right? You should be able to predict that. And then kind of going along with that is, like, do we have free will or not? I don't know. That's like another thing, right? Like the words that that are coming out of my mouth right now are the results of like these electrical impulses firing in my brain. And if you kind of trace all of these back, like my neurons and those electrical impulses are just reacting to like stimuli and things like that. And so, I don't know, there's kind of a side question about that, right? Like, do we have free will, or is everything truly just kind of predetermined, right? And there does seem to be something where there is kind of like true randomness at the quantum level, or at least that's how it seems. We don't have anything to further explain stuff that's happening at the quantum level and like when particles decay and stuff like that. But I don't know. This is just kind of a on a broader level. There's a question of just like what is random, and so we're going to kind of treat our computer's ability to generate random numbers, and we're going to kind of accept that as like quote random, even though they are what we consider pseudo random number generators. There are other. I think there's random.org, and I think some of these places actually use like weather-related phenomena to try to generate the random numbers, so that there's kind of like this constant actual random, something tied to the physical world. But anyway, our computers use what we call pseudo-random number generators, and this is basically a deterministic way to generate a sequence of numbers that at least appears random, okay? They are not random as if you give it the same set of starting conditions, they will always produce the same sequence of numbers, okay? However, when you kind of look, if you don't really know the starting sequence or starting conditions, and you just kind of look at the stream of values that it produces, this stream of values behave a lot like truly random values, okay? And this topic of pseudo-random number generators was an important area of research for like several decades. And then we finally came to what we call the Mersenne twistor, which is kind of the gold standard today. And it's so good that this is now almost treated like a solved problem. And there's not a ton of research being done in random number generation. Not a ton of research being done here. Maybe for like cryptographic applications a little bit, but more research is done on kind of like the security and encryption side, where random number generation is not as key as it used to be, okay? And so let me just kind of start off with like the early days, okay? So one of the earlier random number generators was what we call the linear congruential generator, okay? So one of the oldest and I guess well-known methods for generating random numbers. And basically the way it worked was you have kind of your current number, okay? X at time n is your current random number, all right? And perhaps, you know, you'd have your starting seed, whatever it is, that would be your X at time 0. And then you would multiply that number by A, some constant A. You would add another constant C, and then you would mod M. So you would basically divide by some number M and get the remainder. And whatever remainder you got, that would be your next random number, okay? So this is a terrible, terrible example, but let's just say you started with number 1, and then your constants were A is 2, C is 0, and M is 9. So the way this would work is you would do 2 times 1 plus 0 mod 9, so that would give us 2 mod 9, and that gives me the value 2. Then I plug in 2, and I would get 2 times 2, and I get 4. 4 mod 9 is 4, and then I would get 4 times 2 is 8. 8 mod 9 is 8. And then I would do 8 times 2, and I would get 16. 16 mod 9 is 7. 7 times 2 is 14. 14 mod 9 is 5. And then 5 times 2 is 10. 10 mod 9 is 1. And then we're back at the beginning, okay, with 1 times 2 is 2, and 2 mod 9 is 2. And so, you know, my sequence would be 2, 4, 8, 7, 5, 1, and then it would cycle around 2, 4, 8, 7, 5, 1. Okay, so this is very bad at generating random numbers, but you know, there's when you do something like this, you get kind of a sequence that if you didn't quite know what was the algorithm happening, right? If I just showed you, like, if there was like if we had a brain teaser, and I said, here's your sequence of numbers, 2, 4, 8, 7, 5, and I said, predict the next number in the sequence, I think we would all have a bit of it would be a pretty tough brain teaser to solve, right? You know, like if you got like 2, 4, 8, and I said the next number, you'd probably say 16, that would be simple, but if you get 2, 4, 8, 7, 5, 1, then that would be a lot tougher to try to solve. But anyway, here's just some basic code to implement that linear congruential generator. I'm going to call it rand, and the output is going to be, we're going to store our output here, and basically we're just going to do 8 times x plus c mod m, and whatever we get, that's going to be our output, and we will append that, okay? And so if I say, hey, give me 12 numbers from this thing, we get exactly what we get, 2, 4, 8, 7, 5, 1, and then 2, 4, 8, 7, 5, 1, and the cycle keeps going. This linear congruential generator has been studied for quite a while, and so certain number combinations have been found to have pretty good performance, okay? And so if you use this big number, all right, so remember it's a times x plus c, okay? Then if you use these numbers, a times x plus c, and then and this is you're doing mod 2 to the 31, it generates a whole bunch of numbers that look like this, okay? And if you scale everything down by 2 to the 31, so that because that's the mod that you're using, so everything comes out between 0 and 1, you get something that looks kind of close to a uniform distribution, okay? Fairly close to a uniform distribution after 10,000 values or so. If you look at the empirical CDF of what you've generated versus the actual thing, so the theoretic CDF is the straight red line, and then the empirical CDF is in black. You get pretty close alignment, and this would be the so if you kind of pick up the original copy of the C language and you use the random number generator in the C language, it was the linear congruential generator with these kind of parameters, all right? And this is how it would generate your numbers, okay? and that's how it worked. Okay. However, today the kind of most popular random number generator is called the Mersenne Twister. All right, and it is the default algorithm choice in R and Python, MATLAB, versions of C++, a whole bunch of other languages and things like that. And it was developed, close to 30 years ago, 27 years ago now. All right, and it uses, I guess, what's called a Mersenne prime, 2 to the whatever number this is, 19,937 minus 1. Okay, and the algorithm for the Mersenne Twister is fairly complicated, beyond the scope of the course. I tried to read the paper that describes the algorithm, but it's yeah, it's hard. They basically, every number it generates, it also does like some bit shifting, which is, really just multiplying or dividing by a factor of 2 or power of 2. But anyway, this thing has been created. It's fast. It performs very well. All kinds of statistical tests have been performed on it to say, like, does this act like truly random numbers? And pretty much it's passed all of these tests. So we say, all right, this is good enough, and we haven't really done too much more research. I mean, yes, some papers are being published, but a lot of people just use the Mersenne Twister. Now, one thing to note is that the Mersenne Twister is not cryptographically secure, in that if you see a sequence of numbers generated by the Mersenne Twister, once you see a certain number of values being generated, and if you know it's coming from the Mersenne Twister, you can kind of figure out where in the random seed, like what your random starting seed was, and then you can, once you know your starting seed, you can start figuring out like what numbers are going to be predicted next. So in that regard, it is not secure, but as far as treating it like random numbers, it works. And so we're going to just kind of assume we have a way to generate random uniform numbers. Okay, and whether we're using a simple algorithm that we understand, like the linear congruential generator, or we're using the Mersenne Twister, which we won't understand, not in this course, but we're going to kind of just move on from here, assuming we're able to generate numbers, random numbers, from the uniform distribution. Okay, let me give you your first view quiz answer for today, which is the letter C, C as in cat. Okay, so the rest of this lecture and the rest of our week is going to focus on generating values from different random distributions, and we're going to assume that we are able to start with generating values from the uniform distribution. So that is a uniform distribution going from 0 to 1. Our PDF is basically 1 for all values between 0 and 1, so that we have an area, basically a square with area 1, and it's 0 everywhere else, okay? And as far as R goes, we can use RUnif, and then you can always look up in R, you can always look up a little bit more on the help, and there are different choices here. So here is RUnif, and then you can also, where is help on random? C, okay, so see also RNG, random number generation, and the default, so the default is the Mersenne Twister, okay? But if you want, you can read up the other random generators that we have. So we have Witchman Hill Marsaglia Multicarry, the Super Duper, Mersenne Twister, the Knuth Teo CP 2002, I don't know, whatever these things are, okay? So there are different random generators, and you can also supply your own random number generator. But but the default that we use is Mersenne Twister, and that's going to be the default number generator for a lot of applications. Okay, So our first kind of method to generate random values from a different distribution, okay, is the inverse CDF method, or the inverse transform method. And basically, we take the CDF function, the inverse of the CDF function, and we do that to generate values from a probability distribution. So basically, if you think about, okay, what is the definition of a CDF, all right? So the definition of the CDF, cumulative distribution function, is that it's the probability that the random variable is less than or equal to some, value x, and that's found by taking the integral from negative infinity to that value of x, basically the PDF of, t dt, okay? And so this is going to map basically the entire support of x, wherever it is, to the interval 0 to 1, okay? You can read more on Wikipedia about the inverse CDF method. So, if a continuous random variable x has the CDF f of x, then a random variable that we'll call u, defined as this value u of f of x, this value is going to follow a standard uniform distribution. So if you generate random values of x coming from, this PDF, and it has this CDF, and you just kind of plug it in, it's going to map values. Remember, the range of the CDF is 0 to 1, okay? And basically the distribution of random values of this thing is going to be the uniform distribution, okay? So the function big F of x transforms random values x into basically the uniform from 0 to 1. So if you start with a value from the uniform, you can use the inverse to kind of map it back to x. So basically, if you think about, let's say we generate random values from the normal distribution, okay? And then we think about what the CDF of the normal distribution is. So what is the probability that a random normal value will have, standard normal, will have a value of 0 or less, okay? We would say 50%, okay? And if you plug in 0 into the CDF of the normal, you would get 50%, right? If I say, hey, what is the probability that a random normal value is, 1.96 or less, okay? And you'd say, okay, well, that's corresponds to the, 97.5 percentile, so 97.5%. And then if you plug in 1.96 into the CDF of the normal, you'd get 0.975, right? And it's going to be true for basically any other value in the normal distribution. If you say, all right, what is the probability if I'm going to generate a random normal value and I plug it into this, you're going to get basically a value between 0 and 1. And if you look at all of those probabilities, they will follow the uniform distribution. So the idea here is we're going to just take that property and kind of reverse it to get our inverse CDF. So if we have a continuous random variable that has this CDF, big F, then the inverse CDF is defined as this. We just take the inverse of F, okay? We plug in a random uniform value, U, okay? And basically the smallest value such that big F of t is greater than that value U, okay, is going to be that quantity will follow these prescribed distribution that we want, okay? So if U comes from a uniform, then the inverse, that is F inverse of U, will come from the desired distribution F of x, okay? And so, yeah, this thing just means the smallest value of t that satisfies this criteria that F of t is greater than or equal to U. All right, let's just kind of, I guess here's the proof, and then we'll try out some examples to try to demonstrate how this works. Okay, so to kind of prove that this method works, we'll look at the distribution result of putting a random uniform number into the inverse CDF function, all right? So if I plug this in, okay, then what we want to know is, okay, well, what is the probability that the inverse of f, okay, applied to our random uniform is going to be less than or equal to x, okay? All right, and so this is going to be equal to this. The probability of this, so, all right, what is, if I can apply the CDF f to this, okay, and this seems kind of stupid, but all right, when you apply the function, the CDF of f to the inverse, you're going to just get back u, and on the right-hand side, you're going to get the CDF of x, okay? And by definition, what is the probability that a uniform value is less than the CDF of x? That is by definition what is, what is the probability of this is going to be just equal to that, right? The probability of some uniform value being less than some quantity is by definition that quantity itself, okay? And so so there's our solution, that this indeed is going to generate values from the distribution, desired distribution x, okay? So if x has CDF-f, then generating, taking the inverse CDF and applying it to random uniform values will produce values that come from this distribution x. So this is how it's going to work. We're going to kind of, first, the hardest part is deriving the inverse CDF. So some functions, it's very difficult to take the inverse of. Some functions we don't even have a closed form solution for the CDF. So in that case, like, this method's not going to work. But assuming we have a function for the CDF and assuming we can invert it, okay, take the inverse of it, then once you have that, you just generate random values from the uniform, plug them in, and then your values x will be coming from the desired distribution, all right? So, so this is going to work for any distribution as long as this function, the inverse of the CDF, can be found, okay? And it will also work for discrete distributions as well. Okay, so let's just try a couple examples. All right, so one of the simplest is, what if you just want to go from uniform on the interval 0 to 1 to some interval a to b, okay? So instead of so if we go from 0 to 1, this is our CDF, okay, 0 to 1. Maybe we want to generate, a different set of values, right? So what if we want to go from, say, 0 to 100, right? Well, it's, I think you would just do this very simply in your head, right? Like if I say, all right, I want you to transform values going from 0 to 1 to 0 to 100, you would just say, all right, well, give me your random uniform value, and I would just multiply it by 100, right? Like, we could do that in our head, and that's exactly what we would do here, okay? Is if we think about what is the CDF of this thing, okay, it's just going to be basically this whole thing kind of stretched out, right? And the total area of the total area of the PDF has to be 1, but this thing is still going to go from 0 to 1 here, right? And we're ending up at 100 over there, okay? And so if we think about, okay, well, what is the CDF? We're going to do x minus a divided by the width here. In our case, a is 0, but we're going to just do x divided by 100 in this case. Or I guess, alternatively, if we have another thing and I say, generate values from, say, 50 to 100. How would that work? Right? Well, what you would do is you would multiply your random uniform value by 50, and then you would add it to 50, right? Okay, and then that would generate values, right? And that's basically what we're going to do here, right? So when you take the inverse of your CDF. So when you calculate the CDF, it's going to be from a to x, and then your PDF is 1 over b minus a, and then you're going to get this quantity, x over b minus a over b minus a. So you're going to get this thing. This is your CDF. All right. And then to inverse, you're just going to say, all right, we're going to set this thing on the left equal to u, and we're going to multiply by basically the width between b and a. Right? So whether that's 100 or 50, we're going to multiply that by this, and then we're going to just kind of shift things up. So if we are talking about generating from 0 to 100, we would just take our random value, our random uniform value, multiply it by 100, and then we wouldn't add anything. Our a is 0. We would start there. Okay? If we're generating values from 50 to 100, we would multiply our random uniform by 50. Okay, and that's going to generate values from 0 to 50, and then we're going to add on 50 so that everything has been shifted forward from 50 to 100. And so this is how you would generate random uniform values from just a different interval a to b. All right, let me give you your next answer, which is the letter D. D as in dog. D as in dog. Okay, so, all right, just for example, if we're generating values from 10 to 20, okay, when u is 0, okay, basically this is our algorithm. So if the random uniform value produces 0, then our value will be 10. If the random uniform value produces 1, then our value is 20. If the random uniform is 0.22, then that would correspond to the value 12.2. If the random uniform is 0.5, that would correspond to 15, so on and so forth. Okay, what about this? Here is an exponential distribution, right? So the PDF of the exponential distribution is this, lambda e to the negative lambda x. So this is a PDF. And then the CDF looks like this, okay? 0 to 1. And then we want to take the inverse of this, okay? So the inverse is going to look like something like this, right? So the we get 1 minus e to the negative lambda x if you integrate this. So integrating from 0 to x, I mean, you know, because everything is, our PDF starts at 0 for exponential, okay? This is what our CDF looks like, okay? And then so if you take the inverse of this, right, basically you're going to set the left-hand side, the CDF, equal to u, and then you're going to try to solve in terms of x. So we're going to do 1 minus e to the negative lambda x is equal to u, and then we're going to try to solve in terms of x, okay? So if I do 1 minus e to the negative lambda x, I'm going to add, subtract 1 from both sides, and then I'll multiply it by negative 1. I get e to the negative lambda x, 1 minus mu, and then I'll take the 1 minus u, and then I'll take the log of both sides, and I'll get negative lambda x is equal to log of 1 minus u, and then divide both sides by negative lambda. So I get x is equal to negative 1 over lambda log of 1 minus u. Now, the quantity 1 minus u has the same distribution as u. Right? So if u is random uniform, then the quantity 1 minus u also has a random uniform distribution. So a lot of times you will see, rather than directly solving x is equal to negative lambda, 1 over lambda log 1 minus u, you'll just see negative 1 over lambda log of u, because the random variable u and the random variable 1 minus u are both going to be random uniform values here. So this will be our inverse CDF method, okay? And so here, the quantity, so if this is theta 1 over lambda log of 1 minus u, and then over here is kind of the opposite over here. 0 to 1 of, this is going to be log of u. Okay, so if I plug in, say, 0, okay, log of 0 would be kind of negative infinity, and then, or negative log 0 would produce infinity. So we're looking at the quantity on the right. If you plug in all the way at 1, you're going to get 0, and then basically values in between. So if you generate 0.1, so this goes up to infinity, but say at 0.1 you're at 2.3. At 0.5 you're at 0.693, and then at 0.9 you're at 0.105. Kind of corresponding to these different random values. And these would correspond to values coming from an exponential distribution. Okay? And so just to kind of demonstrate that that is indeed the case, this is going to be our algorithm is I'm going to just generate random uniform values, okay? And then plug it into this thing, negative log of u, and then we can plot this out, okay? So here I'm going to just generate 10,000 random uniform values, and then we'll plug this into the function negative log of u, okay? And that's going to be my x values, and we can see this produces indeed what looks like an exponential distribution. So the exponential distribution, the PDF looks like this, and indeed that's what it looks like. Here I've plotted the actual PDF in red. In red I have the PDF, and what we see is that the histogram in gray aligns quite closely with the actual PDF in red. And here I've plotted the CDF, okay, in red along with the empirical CDF in black. And we can see there's close alignment between the empirical CDF and the theoretic CDF in red. Okay, so these two things align very closely, indicating to us that, when we generate values from the random uniform and we apply the inverse CDF transform, which is basically taking the log, we're getting exponential values, okay? Now, there is a statistical test. Rather than just kind of going off of, our gut feelings and stuff and just saying like, okay, that looks pretty good and this looks pretty good, you can actually do some hypothesis tests, all right? And so one of these is the Kolmogorov-Smirnov test. Have you guys learned about this in other classes? The KS test, Kolmogorov-Smirnov? Okay, well, this is it's a test to see if values, either it could be like two samples, did they come from the same distribution, or did one sample come from some theoretic distribution? Okay, that's how it can be done, and you do this. So in our case, we want to test if our random values x came from a theoretic distribution. So our theoretic distribution, you have to provide the CDF of the theoretic distribution. So that's the exponential. You give it a function name. So in our case, we have the CDF of the exponential. So that's going to be p exp with a rate of 1, and then we plug in our random values x, and we get a p-value that's greater than 0.05. Okay, and so this just means right now we don't have evidence to say that our values are coming from a different distribution. So, like all hypothesis testing, so you never get to prove the null hypothesis is true. You can only say, I don't have enough evidence to reject the null hypothesis. And right now, our null hypothesis is that it comes from this distribution, and the alternative is that it comes from a different distribution. And right now we don't have evidence to say our 10,000 values are coming from a different distribution, okay? But again, we can never say this proves that our values come from the exponential distribution. We just say we don't have evidence to say that it comes from a different distribution. Now, there's a few limits, is that the KS test, once you get like too big of a sample, then everything is going to come out to be significant. Like you're going to get a tiny p-value. But 10,000 values, it's okay. But if you start pushing it to like 1 million, okay, like at 1 million values, then almost any slight deviation, it's going to say, all right, it's not coming from the distribution there. Okay. The way R actually generates values from the normal distribution is using the inverse CDF method, okay? Which sounds kind of strange because you're like, I thought we don't even have a closed form solution for the CDF, much less a closed form solution for the inverse CDF. And that is true. And I said, the inverse CDF method will work as long as you have a function to give us the inverse CDF. But the thing is our computers, when we ask for the CDF of the normal distribution, it just has an approximation, okay? So the CDF of the normal function, of the normal distribution, in reality, does not have a closed form solution, okay? But what we do have is we have an approximation that's really good. And that approximation is accurate to 16 decimal places. And that's the limit of what our computers can even compute anyway, okay? So is it 100% accurate approximation? No, it's not. It's an approximation, okay? And, if you talk to a pure math person, pure math people don't like approximations. But as far as computers go, and we go, okay, well, it doesn't matter because all of these decimal places don't matter anymore, then it's fine, right? It's because like if you ask your computer like what is pi, it only gives it up to 16 decimal places. And then if you were to say, well, this is the actual value of pi, all the mathematicians would get angry. But as far as the computer goes, that's good enough. And so we have a normal CDF approximation that's good enough to 16 decimal places. And we have an inverse of that function that's good enough to 16 decimal places. And we use that to generate our random normal values, okay? So p-norm and q-norm provide approximations that are accurate to 16 decimal places. And so when you use r-norm, okay, R actually generates values from the uniform distribution, and it just plugs it into our inverse CDF approximation, okay? And that gives us things that look like random normal values, accurate up to 16 decimal places, okay? And I can prove this, so, or at least kind of demonstrate. So if I do set seed 1, and I say, give me 5 random uniform values, okay? R kind of does this funny thing where it just kind of uses only every other value, but you can see this is the random uniform value, 0.26550866, whatever. And if I take that number and I plug it into q-norm, okay, it gives me the value negative 0.626, okay? And then, for whatever reason, R only uses like every other random uniform value. And then, so if I take this value over here, 0.57285, and I plug that in, okay? So the inverse CDF of 0.5 would be 0, and here we're at 0.57, and so the inverse CDF is 0.183, right? And then over here, this is the last value, 0.2016, and if you plug in 0.2016, this is the value you get, okay? And so if I reset my seed, and if I say set seed 1, okay, and I say, hey, give me 3 random normal values, you get these same exact values, negative 0.626, 0.183643, and negative 0.8356, whatever this is, okay? So this is basically what R is doing. When you ask R norm, it is really, under the hood, generating our uniform, throwing away some of the values, and then taking these values and plugging it into the inverse CDF. So the density of the normal distribution is d norm. The cumulative distribution function, the CDF, is p norm, and then the inverse CDF is q norm. And we're just plugging in random uniform values into q norm, and that's going to give us values that are normally distributed. And that's what's happening here. Okay. All right. And that is our introduction to inverse CDF method. And so we'll wrap things up here, and then let me give you your last view quiz answer. Let me stop.